Welcome to the lesson on operations on real numbers. At the end of this lesson, you will be able to perform different mathematical operations on real numbers, represent the square root of a real number on a number line, and list the identities related to square roots. You'll also be able to rationalize a number whose denominator is an irrational number. A real number is either a rational number or an irrational number. When we add, subtract, or multiply two rational numbers, we get a rational number. Even when we divide one rational number by a non-zero rational number, we get a rational number. This implies that rational numbers satisfy the closure property under these operations. But this is not the case with irrational numbers. Let's have a look. On adding 3 plus the square root of 2 and 3 minus the square root of 2, we get 6. On subtracting the square root of 3 from the square root of 3, we get 0. Similarly, if you multiply the square root of 2 by itself, then you get 2. If you divide the square root of 3 by the square root of 3, then the quotient is 1. Here in all the cases, the obtained results are rational numbers. Thus, irrational numbers do not satisfy the closure property under these operations. Also, real numbers satisfy the commutative, associative, and distributive laws. Let's recapitulate them quickly. The commutative law states that numbers can be added or multiplied in any order. The associative law states that in addition or multiplication numbers can be grouped in any order. The distributive law involves both addition and multiplication of numbers. What do you get if you add or multiply a rational number with an irrational number? We know that the square root of 5 is an irrational number. That is, the decimal expansion of the square root of 5 is a non-terminating, non-recurring. On adding this non-terminating, non-recurring decimal to 3, we get a non-terminating, non-recurring decimal. Similarly, on subtracting an irrational number from a rational number, we get an irrational number. Thus, we conclude that the sum or difference of a rational number and an irrational number is an irrational number. On multiplying the square root of 5 by 3, we get an irrational number. Similarly, on dividing a rational number by an irrational number, we get an irrational number. Thus, we conclude that the product or quotient of a rational number with an irrational number is an irrational number. Can you represent the square root of a real number on a number line? First, let's consider the square root of 4. We know that the square root of 4 is 2. OA represents the square root of 4 on the number line. Now, can you represent the square root of 2.2 on the number line? To determine its position on the number line, we first find the value of the square root of 2.2. We'll find it geometrically. First, we'll mark the distance 2.2 on a line. Let's represent this distance as AB. Next, we mark a distance of 1 unit from B and represent the point as C. Let's represent the midpoint of AC as O. Now, we draw a semicircle with the center O and the radius equal to the measure of OA or OC with the help of a compass. We draw a line through B perpendicular to AC with the help of a protractor. Let the intersecting point of the semicircle and the perpendicular line be denoted by D. The distance BD is the square root of 2.2. To represent the square root of 2.2 on the number line, measure the distance BD with the help of a compass. Mark an arc OE equal to BD on the number line. Thus the distance OE represents the square root of 2.2 on the number line. Similarly, we can represent any positive real number x on the number line by finding its value geometrically. You can perform this by taking a point P such that AB is equal to x. Then the distance BD is equal to the square root of x. This result can be verified by using the Pythagoras theorem. Let's join the points O and D. Here the triangle OBD is a right angle triangle. Now OD is equal to OC, which are the radii of the circle. Since O is the midpoint of AC, OD is equal to AC divided by 2, which is equal to x plus 1 divided by 2. Now OB is equal to AB minus OA. Substitute the values of AB and OA. Let's simplify this. Thus, OB is equal to x minus 1 divided by 2. Applying the Pythagoras theorem on triangle OBD, we have OD square is equal to BD square plus OB square. This can also be written as BD square is equal to OD square minus OB square. Let's substitute the values of OD and OB in this equation. Let's simplify this. Thus, BD is equal to the square root of x. Therefore, we can conclude that the square root of any positive real number exists. Identities related to the square roots are useful to simplify numeric and algebraic expressions. Here A, B, C, and D are positive real numbers. The first identity is the square root of AB is equal to the square root of A multiplied with the square root of B. Let's verify this with the help of an example. Here the square root of 4 multiplied with 9 is equal to the square root of 36, which is equal to 6. Similarly, the square root of 4 multiplied with the square root of 9 is equal to 2 multiplied with 3, which is equal to 6. Thus both the sides are equal. The second identity is the square root of A divided by B is equal to the square root of A divided by the square root of B. Let's take this example. The left-hand side of the example is the square root of 16 divided by 4 equal to the square root of 4, which is equal to 2. Similarly, on simplifying the right-hand side, we get 2. Thus, it is verified. The third identity is the product of the sum and the difference of the square root of A and the square root of B is equal to A minus B. Let's verify this. Now, simplify the left-hand side by expanding it. These two terms get cancelled. Now apply the first identity. Let's simplify this expression. On simplification, we get 1. And the right-hand side is equal to 3 minus 2, which is equal to 1. Thus, both the sides of the example are equal. The fourth identity is A plus the square root of B multiplied by A minus the square root of B is equal to A square minus B. Now, we'll verify this by using an example. Let's first simplify the left-hand side of the example. Now expand the expression. These two terms get cancelled. On applying the first identity, the expression becomes 9 minus the square root of 4. On simplification, the left-hand side of the example is equal to 9 minus 2, which is equal to 7. Now, we'll simplify the right-hand side of the example. On simplification, we get 9 minus 2, which is equal to 7. Thus, both the sides of the example are equal. Now let's verify the fifth identity by using an example. First, we'll simplify the left-hand side of the example. Then expand the expression. Let's simplify this by using the first identity. This is equal to the right-hand side of the example. Thus, it is verified. The sixth identity is the square root of a plus the square root of b whole squared is equal to a plus 2 times square root of ab plus b. Let's verify it. Let's first consider the left-hand side of the example. Now we expand this expression. Apply the first identity and simplify this. This is equal to the right-hand side of the example. By now, you're aware if the decimal expansion of the square root of a number is non-terminating, non-recurring, then the square root is an irrational number. You can also represent them on a number line. Can you visualize 1 divided by the square root of 5 on a number line? This can be represented on the number line if we can write it in its equivalent form with the denominator as a rational number. Let's try to simplify it. Here the denominator is a square root of a real number. To simplify this, you can apply the appropriate identity involving square roots. This process is called rationalizing the denominator. Let's rationalize the square root of 5. We know that if we multiply the square root of 5 with the square root of 5, then the product is rational. Now, we'll multiply the numerator and the denominator of the expression with the square root of 5. This is the equivalent expression, where the denominator 5 is the rational number. Now, we can easily represent this on the number line. This lies between 0 and the square root of 5. Let's recap. The sum, difference, and the product of two rational numbers is always a rational number. The quotient of a division of one rational number by a non-zero rational number is a rational number. Rational numbers satisfy the closure property under addition, subtraction, multiplication, and division. The sum, difference, multiplication, and division of irrational numbers are not always irrational. Irrational numbers do not satisfy the closure property under addition, subtraction, multiplication, and division. Real numbers satisfy the commutative, associative, and distributive laws. The sum or difference of a rational number and an irrational number is an irrational number. The product or division of a rational number with an irrational number is an irrational number. Here are the identities involving square roots. The process of converting the denominator into a rational number is called rationalizing the denominator.